So basically today's session is all about fundamentals of network security, and we would like to assume that many of you are comfortable with certain security concepts, but this covers just the fundamentals. And if you have any questions or if there are topics that are not covered in the slides, please feel free to ask me on the chat. I will try to answer as much as possible. Even if you have questions that are not related to the slides, feel free to type in your questions and I will be more than happy to answer your questions. Right? All right, starting. So, just an introduction about who I am. My name is Tashi Phuntsho. I'm a senior training officer here at APNIC. My email ID is tashi@apnic.net. Feel free to drop me an email if you have any other issues, real life problems, networking issues, and not only security related. If you have any routing related issues, feel free to write to us and I'll try to get back to you guys as soon as possible. Right. Moving on. And for us to help improve our delivery, and I would request that at the end of this session, I would request if you guys could fill up the survey. Once the survey is filled up, I will share the FTP link from where you can download the slides if you need it. Right? So moving on, here is the agenda for today's talk. Basically, we will talk about why the need for security in the first place, which I'm pretty sure most of you already know. Then we will look at not all attacks, but some of the attacks that are possible on the various layers of the OSI stack or the TCP/IP stack. Then we will probably discuss two very simple attacks, which would be DNS cache poisoning and also, if I'm not sure, I think we will mostly look at that, and also some TCP attacks, the SYN floods, we will look at that. Then we will talk about how to build trust in your own network, how the predominant model of security is in the current market. Then we will touch briefly on cryptography and public key infrastructure, and also VPN and IPsec, and then we will talk about the importance of the APNIC database when it comes to security incidences, right? So, why security? So, not to spend so much time here, I think what's very important is the slide actually goes back a bit to history by saying that internet initially, when it was conceived, I'm sure all of you know internet was designed solely to connect two trusted sites, right? University networks, Department of Defense networks, and they were trusted networks. And to connect them, the internet was solely conceived for that purpose. And primarily, I believe that could explain why security was never considered initially when internet was conceived. So now the problem with that is, as internet became so scalable, as it gained so much popularity, now the problem is we realize there are security issues with it. And that's why security protocols are more of a patchwork that's built onto the existing TCP/IP or the OSI stack, right? But basically, what's important when it comes to security, again, I think what's important is to understand that no security solution is applicable to everyone, meaning security has to be per organization or per individual or on a per need basis. But most importantly, the way we see security right now, primarily security at the moment is concerned with, because of the ubiquitous nature of the internet, and primarily concerned with people not being able to exploit your data, whether it's confidential or not. I really don't like the word confidential data because I believe every data is confidential for you, which could be exploited by others. The fundamental aspects of information that must be protected, as you can see on the slide. This is just to give you an example of some of the data that needs to be protected. But a very important takeaway from this slide is, please do not assume. I think the biggest security risk in our age is when people say that since I don't have any interest in traffic, maybe I'm just a very small organization, and people assume that no one is going to attack you. People assume that it's only banks or it's only big organizations that might be target of malicious attackers. But that, I believe, is the biggest security risk other than any other risk that we have. Because let's say you are even if you are a home user, I could exploit you. I could connect to your network and launch attacks from your network. So that assumption that you are not interesting enough for anyone is, I think, the biggest issue that we have currently, right? Moving on, just to give an overview of the evolution of internet. Initially, those days when the internet was primarily designed, like I said, it was designed to connect trusted networks between each other. So LAN segments which were not connected to the internet, primarily two different LAN segments connected to each other. So security wasn't much of an issue and wasn't given much of a thought anyways. But gradually in the last decade or so, as people's computer literacy has improved, data has become much cheaper. That transition from voice to a very data specific network growth throughout the world, even in poorer economies, means that security has gotten so much attention, and the fact that everyone uses internet now means that everyone is vulnerable to being exploited, either directly or indirectly. Indirectly by using you as a launchpad to attack someone, and directly if you have very interesting traffic to grab your traffic, right? But also keep in mind here that, again, like I said before, there is no one solution to a security problem. Your security needs might be different to someone else's security needs, right? So there is no one solution for everything, no single formula when it comes to security, right? And the third bullet point I think is very important. Please keep in mind, vendors will keep telling you they will either sell it so much, or they will either, if they don't have a solution of their own, they might say it's not at all a problem. So do not listen to vendors. Find out your own security needs. Do your own internal penetration testing to find out, what kind of data you have, so you know what level of security is required. So relying on vendors to provide you security, I think, is a major problem too. Moving on. So what do we want to actually achieve through information security, right? Basically, the whole idea is, even if our data is, irrespective whether the data is interesting enough or not interesting for someone, the whole idea of security is, fine, somebody intercepts my data, right? But can they make sense of my data? So that's what confidentiality is all about, right? So let's say when I from Australia sends you a message, maybe you're in India, even if someone manages to intercept our data, because internet by design, there is no singular path, there is no dedicated link between you and me. So I might be traversing so many networks where there might be so many governments in between who might want to intercept our data and have a look at it. So even if they do intercept, the idea of confidentiality is, can they make sense of it? So confidentiality's primary goal is to make sure that it's only me, the sender, and you, the receiver, can make sense of the data that we are transferring between each other, right? So meaning no one in the middle or should be able to make sense of that data. When it comes to integrity, integrity is more like a signature, right? Integrity, when it comes to data integrity, it's primarily in transit. Me as someone who is in the middle, I capture your data, I make changes to your data, and I send it across to you. So integrity's primary concern is that no one has actually changed the data that me, the sender, has sent to you, the receiver. So that is the integrity aspect of security, meaning that I can guarantee that the data was not changed while it was being sent from point A to point B. And availability, now confidentiality, integrity, and all other aspects of network security, it has to serve a purpose, right? And that purpose is availability. That summarizes the whole purpose. If I am hosting a service, for me to run my business successfully, the whole idea is the service that I'm running should be available to my end users, right? Somebody might try to disrupt that, maybe my competitors, maybe some governments, maybe some malicious users who are just having fun, or maybe a kid who is bunked up somewhere in his mom or dad's garage, and he's just playing around. The whole idea. So, meaning whatever we do with regards to information security or network security, be it authentication, be it integrity, be it confidentiality, all these things, if their purpose is not availability of resources to authorized users, then security serves no purpose. So that is to say that whatever security measures we put in place, the whole idea of that or the whole end goal of that is to ensure that the services that we provide is available to users all the time, right? So that's just a summary. And okay, now sorry about the animation. We had some problems when we were loading the slides, so that's why we had to stick to a PDF. Someone is just joining in. Okay, so I would assume that you guys are comfortable with the OSI stack and also the TCP/IP stack, and the fact that OSI is just a reference model. It's easier to explain things using the OSI reference model, anyways. So this is a look at what applications are running on each layer, what tools are what applications are running on each layer, and how vulnerable each layer is actually, right? So we'll start from the lower layers at the network access layer with regards to TCP/IP. I'll take it with regards to TCP/IP stack. At the network access layer, we're looking at very normal attacks, very regular and general attacks like ARP spoofing, MAC flooding, which I'm sure you guys are familiar. If you're not familiar, ARP spoofing, basically me as if I want to send data to someone, if I do not know that person's MAC address, I'm not supposed to send. I cannot send data, right? So to look up that particular node's MAC address, what I do is I send out our broadcast, our request with that particular IP address and requesting its MAC address, right? Now the problem with our request is it's a broadcast packet, meaning everyone connected on that LAN segment, sorry, again, someone is joining. So anyone connected on that LAN segment would be receiving the request that I send out, and if someone can send back the ARP reply or ARP response quicker than the actual node that I'm looking at, then they have actually hijacked the whole session. Meaning that particular, let's say if I'm trying to find out the MAC address of IP address 10.10.10.2, and if 10.10.10.3 actually claims to have that MAC address, then all my communication now goes to that malicious user, right? So that's ARP spoofing. And when it comes to MAC flooding, why would somebody even flood the CAM table of a switch is what people ask. So with regards to MAC flooding, the weird behavior of switches is once the CAM table is full, the problem is whenever new frames come in, the switch will actually flood it out to all ports, meaning it then becomes as good as a broadcast frame. So what malicious users try to do is they will first fill up the CAM table with spoofed source MAC addresses. Once the CAM table is full, next time any genuine frames come in, what happens is since the switch will flood it out to all ports connected to that switch, and if an attacker is connected to one of those ports, then he can actually sniff those packets, right? Ping and ICMP flood, very common. I send out multiple pings using spoofed addresses, spoofed source IP addresses to a victim machine, and they have to respond, right? So basically, these things are all basically some ping and ICMP flood is more of a denial of service attacks, DOS attacks. Now moving up at the transport layer, we are looking at TCP attacks. The most common one, of course, being the SYN flood attacks. We will discuss in the next few slides. And we have, of course, attacks at the routing level. And then, of course, at the application level, most of the attacks generally happen at the application level. And the most common ones, of course, are the cross-sites scriptings that we see, phishing of websites that we see, SQL injections. These are very common attacks, right? So moving on, we will look at. We may not be able to look at all these types of attacks because of time limitation, but we will run through a couple of these attacks just to get an idea of how they do it. With regards to TCP attacks, I assume that all of you know how the TCP three-way handshake process works, right? And send a SYN, client-server model basically send a SYN packet. Again, someone is joining. Sorry, guys. So I send a SYN request, I receive a SYN ACK back, and then to complete the connection, to establish the connection, I need to send an ACK back, right? So now with regards to SYN flooding attack, what happens is, now here, what happens is, let's go to the next slide. Now here, just a sec, I don't know why the pointer is here. Just keep it up there. So here, what happens is, whenever I receive a SYN packet from someone, and when I send them a SYN ACK, I have to maintain that state information, meaning that session request information in my memory, right? And memory, as we know, is always limited. So what people generally do is the most easiest attack is this attack. So I will send floods of SYN packets to a target machine. The target machine has to respond to each and every one of the SYN packets that I send with its own SYN ACK. And not only that, it has to maintain the state, the session request, the session details in its memory. So gradually, if I flood SYN packets to that level, it runs out of memory. So what happens is, next time somebody sends a SYN packet, I don't have any memory to actually serve that SYN request coming in. So it becomes some sort of a denial of service attack. So generally, we call this kind of attacks half-open attacks, or half-open connections that are left because of unacknowledged SYN packets, right? This is one of the most common attacks. And if you guys are aware of SYN cookies, actually, if you use SYN cookies, this attack can easily be mitigated. And yeah, the second kind of attack is DNS spoofing or DNS cache poisoning. This slide is more with respect to DNS cache poisoning. So what happens is, again, sorry, because if the animation worked properly, the attack should have come later. So let me try to explain anyways. For the moment, let's focus on a normal DNS query and how the responses come and how a user can actually get to a URL. Now, let's say your client or your browser, on the browser you type in this domain, the example.com domain. If your browser's cache does not have it, the browser sends it to your nearest DNS server. The DNS server looks up its cache. If that record is not there, before it actually looks up at its cache, it will look up at its own resource records to try and find out if it's authoritative for that particular domain. If it is, it will respond you back with the IP address with the resolved IP address of the domain example.com. If that is not the case, every DNS server has all the 13 root servers mapped in it. So it will then send the query to one of the root servers. Sorry guys, again someone is joining in. Yeah, so like I was saying, the DNS server, if it does not find the record in its so many people are just joining in, and sorry guys again. So where was I? Okay, the DNS server, it does not find the example.com record in its record, nor in its cache. So it will have to send it out to one of the root servers. And when it comes to the root servers, they do not necessarily give you the resolved IP address. Instead, the root servers, what they do is they maintain the location of all the top level domains in the world. So example.com is a generic top level domain. So now in this example, the root server will instead give you the IP address or the location of the top level domain for example.com, right? So it will send that IP address back to the DNS server. The DNS server will then query that particular DNS server, the authoritative DNS server for example.com. And then the example.com DNS server will send back a resolved IP address 192.168.1.1 for that particular domain. And then that's how the client will now contact the web server, meaning browse that particular web server. Yeah. Forget the fact that we are using private IP addresses here. This is just for example. Okay. Now, as you can see here, the query ID that we're using 64571, right? 64571. Now, this query ID is actually used by DNS servers to actually uniquely identify a request coming in and a response that's sent out. So that uniquely identifies a particular DNS query session that comes in, right? Now, if there is a malicious attacker sitting somewhere in the middle, and he can randomly keep generating DNS responses with randomly generated query ID, and if before the actual DNS server here can respond, if the attacker who is randomly generating the query ID actually manages to match the query ID that was initially sent out, and if it matches, then the problem is this DNS server will now assume that is the correct response that is coming in. It will update its own cache. The record is cached in its cache, and then it will also send that response back to the client, right? And now here, the malicious user, what it can do is it can say example.com actually resolves to the IP address 1.99. So meaning the client will now direct all its traffic to the malicious DNS server that's sitting somewhere, right? And now the effect of this is not only with regards to this one particular client, but in the future, if somebody again requests this example.com domain, this DNS server's cache already has that previous spoofed response from that malicious DNS server. So not only this client, but all other future client requests will also be sent to this malicious DNS server, right? To that malicious IP address. Of course, this will stop when the TTL, which is when the timer for that particular record expires. But until that time, all client queries can actually be redirected. And since our internet is more of a name-driven system than an IP address-driven system, if somebody can manipulate your DNS records, then they can actually end up doing a lot of damage, right? So this is how DNS cache poisoning works. DNS spoofing is also something similar. With DNS spoofing, instead of the cache, what will happen is probably the attacker will sit somewhere here in between the DNS server, in between the client and the DNS server. The attacker could be sitting somewhere here in the middle. And when the client sends its query, the attacker will try to randomly generate query IDs and try to again redirect or give back a response with the IP address which will redirect the client's traffic. So that is DNS spoofing, and the one that is shown in this slide is actually DNS cache poisoning, which is more dangerous because the attacker is able to even maliciously change or embed a wrong record in the cache of the DNS server, right? Moving on. So with this very few examples as the basis for our today's session, so that's where this concept of trusted network comes in now. Traditionally, or even now, not even traditionally, I think majority of the networks currently only relies on perimeter-based security, wherein we build a wall and then we filter out who can go in through that wall and who can't go in. Yeah, our firewalls at the perimeter. But what most people forget is, if you look at most of the attack scenarios these days, since we as network operators and system admins and security people, we are focused so much on the outside to the inside traffic, which in the security lingo they call it the north-south traffic. What we don't realize is there are more attacks that actually happen within your own enterprise LAN. So we call that the east-west traffic, right? So the traditional way of doing things is I have a firewall at the perimeter. I control who comes in and who goes out, meaning what packets come in and what packets can go out, and that was it. But now, if you have time, please look at GreyNet. GreyNet is a very good tool which is based on the HoneyNet concept. Somebody has found out that more attacks actually happen within your own network, because once I am able to penetrate one network, it's easier to attack those nodes or those servers that are in that network, because then the correlation becomes really easy. I can guess the IP addresses within that network. So we should also actually focus on the east-west traffic and not only the north-south traffic, meaning the outside to the inside traffic, right? And then traditionally we also use IDS, intrusion detection devices or intrusion detection system. But the flaw with this kind of system is with IDS, most of the signature-based IDS that many people use, IDS is totally based on exploits that we already know, right? What about zero-day attacks? How do we program that into an IDS? Exploits that are known, yes, the IDS will detect it, and then we can have prevention mechanisms, or we can do some mitigation works to make sure that exploit does not happen. But the problem is if that exploit is not already known to us, which people in the security community tend to call it as zero-day attacks, then IDS is almost useless, right? So, but there are some people who, instead of relying on signature-based IDSs, they rely on pattern-based IDSs, meaning anomaly-based IDS, wherein if something is out of place, maybe I should analyze that traffic and find out why is it out of place. But for you to do that, you need to thoroughly and properly understand your network to understand what is normal and what is abnormal, right? So anomaly-based IDSs requires you to have extensive knowledge of your network, and also requires you to do extensive data analysis for you to set that particular threshold. Let's say your normal traffic is 10 Mbps, right? A small enterprise. And let's say 95th percentile traffic is around 7 MB most of the time. All of a sudden, if you have traffic that keeps crossing that threshold, then you can assume that something wrong is actually happening, and then you start investigating. So that's a very simple example of anomaly-based IDS systems, right? So instead of doing this, now what is common in most of the enterprise networks is basically people building trust on top of the TCP/IP structure. So meaning this again is based on the fact that if you can actually verify the identity of the packet that is actually coming in authentication, if your door is actually strong enough, and if only people that have the keys can actually enter the door, then majority of the security is already taken care. So that's why these days it's very common to see that people realizing that authentication is the key to security. So there is this concept of strong authentication, which we will see in the next slide, and also there is this concept of public key infrastructure, right? Let's look at this too in detail. And before we jump to that, again, this cursor. Before we jump to that, all this focus is actually on access control, right? And what is access control? Basically, we have a resource that we are hosting in our network, and users need to access that resource, to use that resource, right? So that is what security is all about. Can I guarantee that it's only the authorized user who is accessing this resource? And can I guarantee that the user uses this resource only based on the permissions that particular user has? So access control, in a summary, is all about the right person getting the right access to a resource, and only people with the right permissions being able to do things or make use of that particular resource, right? So that's where the AAA concept comes in. First, you authenticate whoever is coming in. Are they authorized, or do they have the credentials to actually access my resource? Once that is confirmed, what kind of permissions do they have? What kind of authorizations do they have to what can they do with the resource once they have entered our network, right? Me as a system admin, maybe I need access to all the resources in the network. But let's say someone in the financial team or in the HR team, they might need only access to the ERP system. They may not need access to other applications that I'm hosting in the network. So that's to do with authorization. And of course, accounting is more about, can we keep track of who came in, who did what? Because when things go wrong, it's easier for us to actually track who did what. So AAA, this is what the AAA concept is, right? Again, can't explain because of time constraints. We can't go much, but the whole idea is to give you enough idea for you, enough knowledge for you to go ahead and explore it on your own. Talking about strong authentication, and like we discussed, if the main entry is actually strong enough, then we can almost guarantee that no malicious traffic can actually enter your network, right? So instead of only a single password these days, there are this multi-factor authentication schemes, right? And example, the two-factor authentication. The best example would be your bank account. Sorry, wait. You have your ATM pin, the ATM card. You go to the card. That card is your token, and your PIN is your password, right? So that kind of two-factor authentication. And the other example would be again a bank. I try to transfer money to someone. I need to log in with my username and password into the bank's portal. And before I transfer, the bank will send me authentication code either through SMS or something. And so basically, token is something that only me, the user, has. Passwords are your credentials, so you combine this two, so it makes authentication much more stronger, because passwords as such, people can brute force it, or most of us have this habit of writing passwords down on papers and sticking it somewhere, or writing down passwords in our notepads and keeping it somewhere because we can't remember passwords for all the applications that we use. So that's why this two-factor authentication is very important, and it is gaining so much prominence now, right? So if you are running an organization which has sensitive data, I would suggest you implement at least a two-factor authentication. There are multi-factor authentications too. Example, if you guys are APNIC members, our My APNIC page actually uses two-factor authentication. You log in with your username and password, and you can also use one-time password generators to generate a code which you punch in, and then that's how you are authenticated, right? Yeah, this slide basically talks about what I just discussed. So you generate a one-time password. After a certain timer, that password is no more valid. Again, you keep generating. So meaning you're making it difficult for people to actually guess. Not saying that this is totally so strong that nobody can break it, but they might be able to break it. But what you're trying to do is by randomizing and by having such a small timer wherein you use this password for this period, after that this one-time password expires, again you generate a new one. So along with your own username and password, when you use this kind of one-time password generators, what you're trying to do is you're trying to make it more difficult for anyone to try and break into your system, right? You're not saying they can't break it, but all you're trying to do is you're trying to slow them down as much as possible, so that there is no economic incentive in the end for them, and which I think is a very good one. Nobody talks about this when they talk about security. I think security, the best way to tackle security is to make sure that you can take away that economic incentive away from the attacker. If I have to spend so much resources just to get your password, then why should I even spend so much resources? So that's the concept of economic incentive. And these days, the security trend is that not trying to make it hack proof, but trying to make it so difficult that the attackers, after a while, realize that they actually end up spending more than what they can actually gain by attacking you, right? Moving on. Yep, authorization. Basically, like I said before, once I have once I have been authenticated, once I have gained access into the network, whenever I access a particular resource, what kind of permissions do I have? Yeah. To what level can I do? Can I just read that file, or can I also download that file? Can I also modify that file? So that sort of user level permissions, or so like the example that I gave, maybe the HR folks should have very different permission. Maybe your finance team should have very different permissions when it comes to certain documents or certain resources. And maybe your top level executives, maybe they should get They should get full permission to a certain file, but not the normal employees in a company. Me as a network engineer or a system admin, maybe I need full access to all the IT resources and network devices, but not necessarily to payroll documents, which only HR should be having access. So that's just to give you an idea about the authorization aspect of EEE, right? Moving on, this is again summarizing authentication and authorization. A client comes in, first we authenticate. Once the client's ID is verified, the client is given access to the network. But when they are accessing that particular resource, what kind of permission levels or what kind of authority do they have to do what kind of stuffs with that particular resource? So this picture actually summarizes that, right? And yeah, please have a look at this RFC 3552, where it tries to explain the EEE concept. Authentication simply identifies a party, meaning I identify the user. Once that identity is verified, authorization is about what can I do with this resource, right? What permissions do I have? Moving into cryptography, we will not discuss so much because of time constraints, but to give you a, why is this slide like this? But to give you an idea of cryptography, basically cryptography is nothing new. Those days, what's the best example? Maybe those days in Europe, kings and queens used the seal, right? And even in China and Japan, the emperors, whenever they send messages across, that scroll, once the letter is rolled up, they put their seal and then they send it across, right? And when someone receives that at the other end, if the seal is broken, somebody has tampered with the document. If the seal is not broken, that means the data has not been tampered. This basically, that is integrity. The data's integrity has been preserved all the way from the sender to the receiver. So cryptography has been used from olden days itself, and let's say during the First and the Second World Wars, people trying to jumble up information so that nobody can make sense of it, right? Ciphertexts. Maybe you have a code machine, I have a code machine. I'll jumble up some text. I'll send it across. Only you that has the code machine and me that has the code machine can make sense of that particular piece of paper, but no one else. Even if somebody captures our messenger, unless they have one of those code machines, it would take them longer time to break that code, right? And by that time, and like I said, every code is breakable. Everything can be broken, but how long it takes is where cryptography actually comes in. How difficult can I make it for someone to decrypt my message or to break my code? So that is all cryptography is all about, right? So, and definition-wise, yeah, cryptography, primarily, how can I protect my data when I send it over the internet, which is untrusted domain. So, meaning anybody could be listening there, anybody can capture your packet, anybody can look at your packet. So, instead of preventing that, which is almost impossible. So, what cryptography concerns itself is, even if someone captures it, can they actually read my data? So, we are trying to make sure that nobody can read the data other than me, the sender, and the receiver at the other end, right? Crypto analysis is basically about, if I get an encrypted code, I try to break that code and make sense of the data that I captured. Very common during the Second World War, where the British tried to break the German codes. So all I'm trying to say here is that it is not something new. People have been doing this from ages, but now it is more relevant in our age because of the ubiquitous nature of internet, right? So basically, what this formula tries to tell you is, how do we encrypt the data, right? So ciphertext is the encrypted data. So I take a plain text represented by P, with or without a key. If there is a key, I take the plain text and the key, and I generate a function out of that, which cannot be which no one else can make sense other than you and me, the sender and the receiver, who has access to that particular key, right? So this is how we generate. Of course, the formula here looks very simple, trying to say that your ciphertext is nothing but a function. Why is the slide behaving like this? So unless someone has the key, they wouldn't be able to make sense. They might eventually break it, but maybe it would take them 10 years or 15 years to break that code, and by that time, they would have no economic incentive left, right? Moving on, remember that authentication is a very different, though all authentication, confidentiality, and data integrity is what defines security. We have to understand them differently. They are different parts of the whole security umbrella, right? So encryption and decryption is more to do with confidentiality. Like I said, even if someone gets hold of our data, can they make sense of our data? No. So that's what we are trying to achieve by encryption and decryption, right? Meaning I have a plain text, I encrypt it using a key, then that ciphertext or the jumbled up text makes no sense to anyone. I send it across an untrusted network, let's say the internet, and at the other receiving end, the receiver who has access to that key can use that key to decrypt that message, right? We have two forms of key-based encryption, primarily the symmetric and asymmetric encryption. With regards to symmetric encryption, we use the same key to encrypt the message and also to decrypt the message. So what that means is me, the sender, and you, the receiver, we both need access to the same key, right? So that's why it's called the shared secret key. Right? And the biggest problem in this kind of encryption is key management protocols. Fine, we encrypt with the same key, you decrypt with the same key. Meaning anybody who has access to this key, this particular shared secret key, they can also decrypt this message. So that's why with symmetric encryption, the primary concern is how can we share the key secretly without anybody knowing. So that's where algorithms like Diffie-Hellman DH algorithms come into play. You don't actually share the key between the sender and the receiver. Instead, you use a certain algorithm to generate the same key, to generate that same shared secret key, and then we start encrypting and decrypting using that same key. So that's symmetric encryption, and very common in most of the security protocols. Even in IPsec, you will find that we use symmetric encryption. And by the way, what are the examples of symmetric encryption? You have the, so sorry guys, the slide is, okay. So some examples of symmetric encryption, we have data encryption standards, we have triple DES, and we have advanced encryption standards. Triple DES is supposed to be 3 times more difficult than DES to crack. But AES, of course, is if possible, please try and use AES because it's much more stronger and much more difficult for someone to crack. Right? Asymmetric encryption, with asymmetric encryption, the idea is, we also call it public key algorithm. So the idea is, instead of using a single key to encrypt and also decrypt the message, same key encrypting and decrypting the message, with asymmetric encryption, what we do is we encrypt with one key and you require the other key pair to decrypt the message, right? So both sides, the sender and the receiver, needs to generate a public and a private key pair, right? Then mathematically you can generate them, but the public key is published, the private key you never publish it, you retain the private key, so you need to keep it safe, but the public key you can publish it on public key registries, repositories, or you can publish it on public key servers. So what happens is, let's try to break it down. For authentication with asymmetric encryption, what can happen is, authentication means the receiver knows that Tashi has sent that packet, right? So authenticating me, the sender, is the correct person. So what I could do is, I could actually encrypt. I could encrypt with my private key, and then the receiver could actually decrypt using my public key, and that way the receiver knows that it was me who sent it, because it's only my private key and my public key. So it's only this particular key pair that can encrypt and decrypt, right? So if I encrypt it with the public key, only the private key can decrypt it. If I encrypt it with the private key, only the public key can the other private key private key pair can decrypt it, right? So that way we can achieve authentication. When it comes to confidentiality, if I use my private key, anybody can have access to my public key, so there is no confidentiality. People can read it, anybody who has access. So instead, what I could do is to achieve confidentiality with asymmetric encryption. What we could try to achieve is if I, Tashi, and forget Tashi, let's say Alice and Bob, right? If Alice encrypts the packet using Bob's public key, which can be decrypted only with Bob's private key, and then I encrypt that further using my own private key. So when that message reaches Bob at the receiving end, Bob can use my public key to decrypt my message, knowing that I send it and that no one has modified the data in the past. And for confidentiality, only Bob's private key can decrypt the message that was encrypted with using Bob's public key. I'm sure it must be a bit confusing to you guys, but then please remember that the whole idea with asymmetric encryption is you have a key pair, a public and a private key. Public key can be published, private key you never publish it or you never show it to anyone. And you can do double encryption to ensure you achieve authentication, you ensure you achieve confidentiality, and you achieve integrity. You can achieve all these three using asymmetric encryption. The most common one being the digital signatures. Whenever you download a software, it comes digitally signed, right? That uses asymmetric encryption or public key encryption. So PKI, basically public key infrastructure, it is based on asymmetric encryption, basically. So what it does is, now with public key infrastructure, what we are trying to say is, like I said, it uses asymmetric encryption, but the chain of trust, what public key infrastructure tries to do is it tries to build a chain of trust, right? Example, the HTTPS, the secure web that we try to use, HTTPS. Whenever a browser tries to browse a secure website, I receive that particular web server's digital certificate. But how do I know that somebody in the middle has not sent me that digital certificate and that I received that particular certificate from the correct or the authentic web server? I need to verify that. So for me to verify that, I go up the chain of trust, and that is what is being shown here, where in the components you have the certificate authority or the root certificate authority who sits at the top. It issues all digital certificates and it also signs them using its private key. And then below that you have the intermediate certificate authorities or the registration authorities. The registration authority, you are not allowed to sign certificates, but the intermediate certificate authorities or ICAs, they can also sign authorities for the end entities. And the end entities are your web servers. Example, google.com is one end entity, facebook.com is one end entity, right? So what happens is, let's put it like this. GeoTrust, who is the root certificate authority. Below that is Google ICA, and below that is the google.com web server, right? So when I try to browse google.com web server using HTTPS, that web server gives me the digital certificate of Google's intermediate certificate authority and also google.com web server. So my web browser, instead of believing that, what I will do is I will take google.com's web server digital certificate. The digital certificate contains the public key of the google.com web server. I will take that and I will verify it up. I will go one step up, talk to Google's ICA, look at Google's ICA's certificate, verify that that certificate was signed by it, and again go one step up to GeoTrust. So basically, PKI is a very big topic, but it's a very simple concept if you understand it. You have digital certificates which contain public key. So digital certificates make it easy for you to distribute public keys. So it contains the public key. But to secure it, what we do is we create a hash of that digital certificate. And that hash we encrypt using your private key. That's when we call it digitally signed. So that can only be decrypted using your public key, right? So for you to make sure that the public key that you have received is actually sent by a valid, authentic or a valid entity, we then go up the chain of trust all the way up to the root certificate authority. So this is what public key infrastructure is all about. And if you guys know about RPKI also actually uses the PKI concept, but for resources, the internet IP addresses and the ASN numbers. So that's what RPKI uses. So if you guys get time, please have a look at how, please go through some of the RFCs about PKIs to understand the concept. But it's a very, we don't have, we may not be designing systems ourselves, but we need to at least understand how the PKI concept works, right? So again, a look back at what are the different attacks that are possible. Initially, we looked at what attacks are possible, and now what we are looking at is we are looking at what are the ways or what are the different ways that we can mitigate or fight against those attacks that we saw earlier. At the physical layer, we have, why is the slide like this? Sorry again. At the data link layer or the network access layer, these days, identity-based authentication is very common, 802.1x, because if, let's say you're in a university campus and the university gives you a username and password to latch onto their wireless network, anybody, you could share that with your friends. It could be used anywhere. Anybody could plug in their own access points into any of the ports that are available. So instead of that, what we try to do is with 802.1x, it actually, the authentication, that security is based on your identity, right? Meaning if I try to plug in a particular access point onto any free switch port, unless that is already registered, I cannot use it. So 802.1x is more about identity based authentication. Triple P and PPT, I'm sure most of you are aware. Example, if you use ADSL, you type in your username and password. Before you can use your service, it goes to the AAA radius server at the back end of your service provider. Your username and password gets authenticated, and then only you can browse. So that's the Triple P and PPP TP protocol. IPsec, we will discuss shortly about IPsec. IPsec primarily works at the network layer. So at the network layer, how can we secure packets? How can we make sure the packet, how can we guarantee confidentiality? How can we authenticate the sender and the receiver? And how can we ensure that even if someone captures, nobody can read the packet, right? So we will talk about authentication, integrity, and confidentiality in IPsec. At the transport layer, most common, of course, SSH, SSL, and TLS. TLS is actually based on, not based on, it's a successor to SSL, the third generation of SSL. SSH, instead of telnet and all, you build a socket, and then once that secure tunnel is built, and then you start sending in your terminal commands through the SSH. So that is one way to do. The HTTPS is what we just discussed about. It uses SSL plus public key infrastructure to achieve this. DNSSEC, again, like we saw DNS cache poisoning. How do I know that the DNS response that I have received actually came from a valid DNS server and not someone who is trying to spoof? So for that, we use DNSSEC. PGP and GPGs, again, uses the asymmetric encryption. Let's move on because of time constraints. Sorry, I think we are taking quite a bit of time here because we couldn't start earlier. So, like I said, at the link layer, we have lots of, like we saw in the morning, we were earlier today when we started off, we were discussing MAC flooding, we were discussing ARP spoofing and all. At the link layer, we can also prevent those using dynamic ARP inspection or DHCP snooping concepts. At the network layer, we will look at IPsec, and at the application layer, you have SSL, PGP, SSH, HTTPS, right? So here is a look at, so before we jump into IPsec, let's look at VPNs. So with VPNs, what happens is, let's say you are an enterprise and you want to communicate over untrusted network like the internet. Let's say you are here in Australia and one of your branch offices somewhere else. So how do you securely connect these two sites over the internet, right? So for that we built VPN tunnels. And when it comes to tunnel, I think many people get confused, wondering if you actually build a tunnel, whether people call it logical tunnel or not. Basically, when we say you build a tunnel, what you actually do is, you remember the TCP/IP stack where you encapsulate packets. You started from application layer, you encapsulate that inside a TCP header, you encapsulate that inside an IP header, you encapsulate that inside a frame header, and then you send it down, right? That is just a recommendation. We don't have to follow that strictly. So if we have to follow that strictly, then no VPNs will actually work. That is just a recommendation. And when it comes to VPNs or tunnels, what we do is we can encapsulate it any way you like. I can actually encapsulate, let's say, a frame directly in a, I can actually take a transport segment and encapsulate it directly in a frame. I don't have to encapsulate it in a IP packet directly, and maybe that frame I will encapsulate it back in an IP packet. That IP packet I can encapsulate it back in a frame. So tunneling is all about encapsulations. You play with the encapsulation, and that encapsulation only you, the sender, and the receiver knows how to de-encapsulate that. Nobody in the middle knows. In the middle, routers will only encapsulate in the standard way or decapsulate it in the standard way. If you receive a frame, I remove the frame header to look at the IP packet. I remove the IP header to look at the TCP segment. But with VPN, we encapsulate it in the IPsec header. You encapsulate it in the IPsec header. I send you packets that way. You know how to decapsulate or which header to remove to read the actual packet, right? So that is what VPN is all about. Of course, we have two types of VPN. Remote access VPN. Basically, if you're a mobile user, if you're always on the move, how do you securely connect to your resources in your head office? That's remote access VPN. And then we have site-to-site VPN, where you have two branch offices in two different geographical locations, and you need to connect them securely over the internet, right? This is just, why are the slides like this? Is just to give you an idea about the different VPN protocols. Like I said, we have the PPP. TP point-to-point tunneling protocol, primarily to secure dial-up connections, username and passwords that you send, so that it can be authenticated or it can be verified at the service provider level. If your username and password is valid, then you can use their service, right? Combining PPP, TP, and L2F, the layer 2 forwarding protocol, we have the layer 2 tunneling protocol. But the most common that most people use is the IPsec, which is the Internet IP protocol, or Internet Protocol Security. Right? So IPsec, basically, it works at layer 3. Have a look at RFC2401 described there. Basically, what happens is IPsec, you have two phases of key exchange in IPsec. You have IP phase 1, IP phase 2, which is Internet Key Exchange. In the first phase, I build a secure channel where between the receiver and the sender, we first build a secure channel, and then we exchange what kind of encryption algorithm to use, what kind of key generation algorithms to use. Once that is decided, and once we have shared that information and agreed on that security information, then we build the IPsec tunnel, right? Once the IPsec tunnel is built, anything that we send over that tunnel is very secure, right? So those security parameters that we negotiate are called security associations. Then there are two security protocols in IPsec. You can use the authentication headers, AH, or you can use the ESP encapsulating security payload. With authentication headers, we don't encrypt the packet that goes in the IPsec tunnel, but with encapsulating security payload or with the ESP protocol, we not only build a secure tunnel between the sender and receiver, but we also encrypt the data that actually goes inside that tunnel, right? And of course, the protocol that we use is the Internet Security Association's Key Management Protocol, ISAC-MP. At the transport layer, like I said, we use TLS, we use SSL, we use SSH, right? But again, though these things provide us security, how we implement those standards actually is a major problem. Did any one of you hear about the Heartbleed issue somewhere in 2013, 2012? So the SSL standards implementation by OpenSSL group, they implemented it wrongly, wherein they did no bounds checking, meaning I could actually query a server with a big payload length, and the server would not only give me what I requested, but it would also give me all other data in its memory, and I could look at people's username and passwords that way. So though the standard is there or the feature is there, how you implement it actually matters. So just be careful there, right? And with regards to SSH, yeah, please, instead of using telnets, please use SSH because it actually builds a secure channel between two end devices first, and then you can transfer data securely. To wind up, I think when it comes to security, whatever we spoke right now, we could not even speak in detail. Just to give you a glimpse about what security is all about, what are the tools that are available for you to secure your network. Just remember that the way we started off our today's session, please remember that there is no one fixed solution to a security problem, right? Today we fix this issue. Tomorrow people are who are smarter, they realize that we have patched it up that way, so they will again come up with a newer way to circumvent that, right? They will find some other exploits in our network, so they will try to exploit that. Our job is to make sure that we find out what are the vulnerabilities in our network, make sure that we do not give people, it's like you build a wall and making sure that you don't have weak points on your wall, right? So our job is only that. We can never completely have a secure network unless we disconnect everything, then that is of course very secure. But we can never have a single solution that fits all when it comes to security. So instead, it should be a collective effort, meaning you should have good security policies in your company. Let's say not allowed to use your thumb drives in the office, not allowed to take thumb drives out of the office, right? Not allowed to browse malicious sites, not allowed to bypass your firewalls, not allowed to bypass your proxy servers. Then you should have standard guidelines saying that you cannot take the office laptop out, you cannot bring any external laptops in, that kind of policies, but which everyone has to follow, right? And you can also have policies like, example, what minimum 10 characters. Every password needs to be minimum 10 characters, and you need to change the password every month. So security is a combination of all these things. The security tools you as a network admin or a sysadmin or a security specialist develop, and also the policies that the organization has to follow to make sure that the whole infrastructure is secure. Because you alone as the technical person can definitely not secure an infrastructure. And like I said, it's a very reactive thing. Somebody does finds some weakness in us, we patch up that weakness. And when you combine this policies, standards, guidelines, and your own technical knowledge, all you're trying to make sure is those weaknesses are less. If you had 100 vulnerabilities before, maybe you cut it down to 2 or 3 vulnerabilities. So that's all is there to security. We cannot have a single solution to overcome every security exploit that is there in the market. And this page is put here because the APNIC WHOIS database is one of the most important databases in the region, where we maintain reverse DNS records for all the IP addresses that are distributed in the region, as well as the autonomous system numbers. But why this slide was put here is primarily because whenever an incident occurs, maybe somebody attacks your network, you look up the IP address, you do some analysis, and you find out that this particular IP address has the attack originated from this particular IP address. Then please look up APNIC WHOIS database or other regional internet registry databases. And there you will have all the records. Who is the contact person? If it's administrative, which person to contact? If it's a technical thing, which person to contact? So if you look at IRT, incident response team, so if you have security breaches coming from a particular source IP address, if you look up the APNIC WHOIS database, you will find the contacts of the right person to contact, and you write to them and tell them, look, I'm having such and such attacks from your network. Can you please find out who in your network is trying to do this? So the APNIC WHOIS database is a very useful database when it comes to security incidences. So sorry about that's the end of our session. So sorry we started off very weirdly. maybe I rushed through a few of the slides, and maybe many of you might feel that this session does not cover much. But like I said, because of time constraints, we can't really go so much into depth of each and every topic, nor can we cover every topic. But you have my email ID. I'm more than happy to respond if you guys have other doubts which are not covered in the slides. For now, if you have any questions based on today's sessions, please feel free to let me know on the chat if there are any questions. Any questions? No questions? Any questions, please? Sorry. Does anyone have any question for me? Thank you. Anyone, any questions on any topic? Well, thank you so much for attending, and once again, so sorry for that. I would request you guys to please fill in this survey, the link which is given here, and let us